Welcome back to the free reinforcement learning course from neuralnet.ai. I'm your host, Phil Tabor, and you are watching Module 5A. When we last met, we had just finished covering the theory of dynamic programming. I left to you, dear viewer, an exercise to code up the policy evaluation, policy iteration, and value iteration algorithms. As promised, I'm delivering to you my solution to these algorithms, which we're going to go over in a series of videos. I've decided to split these up because they are a little bit too long for one video. I don't want to have a 20-30 minute video, so we'll split them up into much smaller chunks. Today we tackle policy evaluation, and we are going to do this in the grid world that we created in our series on designing your own OpenAI Gym compliant environments for reinforcement learning. Since we're not going to be doing a game type solution, remember that we already know the state transition probabilities, so we're really just solving a system of equations. Ergo, we do not need all of this stuff in the class that's associated with playing a game. So let's go ahead and gut this thing and get moving. So we do not need the function to add magic squares, but we do need the magic squares. We also do not need the agent position, but we do need the state transition probabilities, which we'll store as a dictionary, and we'll use a function to initialize those values. So we do need to know if it's a terminal state. We don't need to add the magic squares to the grid. We do not need to get the agent row and column. We also do not need to set the state. We do need to know if we're attempting to move off the grid, however. We do not need the step function. Likewise, we do not need reset or the render function. We will use functions to print out the agent's estimate for the value function as well as its policy, but those will be separate utility functions that live outside the class. Let's see, so we do not need this action space sample. We also don't need the max action function because that was for Q learning. We don't need this epsilon, and we also don't need alpha. We will need gamma, and we'll have one other hyperparameter we'll get to later. We don't need the Q dictionary, and we don't need any of this stuff devoted to playing games. We're not playing games, we're solving equations here. All right, so that brings us to our first new function. So we want to initialize these state transition probabilities. Well, there's two ways of doing this. So you can take into account all of the possible combinations between states. So the probability of transitioning from state 1 into state 62, right? That is identically 0 because the agent can only move one step at a time. So aside from the magic squares, of course, which we'll get to in a second, but you could either take into account all possible combinations, or you can simply say we're only going to take into account the combinations that can actually happen within the environment. It turns out it's easier to do that than to take into account every possible combination. So we're going to take the easy route. It's also more clear. So we want to iterate over our states and our possible actions. Now we know that for pretty much every transition the reward is -1 except for the transition into the terminal state, so we can start by assuming the reward is -1. Our new state will be the old state plus the translation we get from the action space dictionary. Now we only have a few edge cases to consider. So if we enter into a magic square, then we have to exit through the exit, right? So that means the probability of going from the entrance to the exit is 1, and the probability of anything else is 0. So if this new state is in self.magicsquares.keys, then the new state is whatever the resulting state is from that dictionary. And that is this. Okay, that's pretty simple. So the next thing we have to consider is if we're attempting to move off the grid. And of course, if we attempt to move off the grid, we fail. So state underscore new state equals old state. Next thing we have to consider is if we are entering the terminal state. And the reason we want to consider that is because not because the probability will be 0, but because the reward is 0. So if is terminal state, reward equals 0. So next we have to assign the this value to the P dictionary. So fun fact about Python, if you're new to Python, dictionary keys must be immutable objects. Lists are not immutable, so you can't use a list as a key. You have to use a tuple. So new state, reward, old state, and action is our key. And of course that value is 1. And that's all there is to initializing our state transition probabilities. Very, very straightforward. Next thing we have to consider is printing the value function and the policy. This is pretty straightforward, so let's handle that first. And these functions live outside of the class because we're going to use a procedural implementation. We don't need any fancy pants classes here. Print v, that'll take the value function and the grid as inputs. And we want to iterate over the grid. Blank and enumerate row. So we're just going to take each row in our grid and then iterate through each column. So if you're new to Python, another thing to note is this idiom here. If you use an underscore and a loop, then that tells the interpreter that you do not care about that value. It's just a dummy placeholder value. You're not going to use it. So that is how we get the state. If you don't believe me, you can check it. So, I'm looking ahead here. So all we want to do is use the correct syntax and print the value. And we can use a tab delimiter instead of a new line. At the end of each row, you want to print a new line, and at the end of the print v function, let's just print a bunch of dashes to make things nice and purty. Next, we want to print the policy. That takes the policy and the grid as input, and we're going to do the same stuff. We're going to iterate. I can copy these 3 lines because they're the same. Can you see? Yes, you can. So if not grid is terminal state, and the reason I'm defining it this way, the reason I have this if statement is because the we're going to be iterating over all of the squares in the grid, but there is no action for the terminal state, right? Once you get to the terminal state, the episode is over. You don't do anything, right? So there's no terminal state in the policy, so we'll get a key error. This is just kind of a kludge. The other thing we have to take into account is we kind of want to print out something different for the magic squares, so that way when we print the policy, it makes more sense. State not in grid magic squares keys. Print string. Good grief. Otherwise, print. We don't want to print, we want to print. In that case, we just want to print a couple dashes. And finally, if we're in the terminal state, we want to print another couple dashes. And likewise, we want to print a new line. Let's do this. Let's copy this from up here and paste there. All right, scroll down. So that is all we need to do for our utility functions. Let's save that. Let's go down to the main loop before we do our policy evaluation, and the reason will become clear in a moment. So the other hyperparameter we need, as we stated in the lecture, is we need some convergence criteria. So the agent's estimate of the value function approaches the true value function asymptotically. That means when you take their difference, you're going to get a smaller and smaller number over time. If you sit there waiting for that number to go to 0, you're going to wait for the heat death of the universe, right? It's asymptotic. It takes forever. So we have to define some threshold where we call it good enough, and that parameter is theta. And 10 to the minus 6 seems to be a pretty good value. We can use that. The next thing we need is the initial estimate for the value function. And as I said, this is arbitrary. Now, just to recall an earlier lecture, we're going to use optimistic initial values here because all of the value function for every state is a negative number at any rate. And so if we bias it with 0 and we had an agent, we would get exploration in any case, even with a purely greedy strategy. And here we want to use the state space plus, not the state space, because we want to take into account the value of the terminal state. Now, as a pop quiz for you guys, what is the value of the terminal state? We'll get to that when we do the policy evaluation. You'll see the answer, but noodle on that for a moment. The next thing we need is a policy. So I was intentionally vague in my assignment, and the reason is you have to learn to deal with ambiguity, and because it's not really a critical point. But the policy can be really anything you want. We're going to improve upon it anyway. So where do you start? One reasonable place to start is the equiprobable random strategy, and that means that for each state in the environment, the agent can move in any of the possible directions with equal probability. In this case, 1/4, because there's 4 moves, so 25% or 0.25. So that means when we create this dictionary, the values will be all of the possible states. And here we want just state space because it doesn't make any sense to move out of the terminal state. env.possible actions. Perfect. So next, now we can swoop back up here and take care of our policy evaluation. So this is a little bit tricky. So what we want to do is we want to check for convergence as we iterate through this loop, and to check for convergence, we need both the old value and the new value of the estimate of the value function. So that new value is given by the policy, right, which is the probability multiplied by the state transition probability times the quantity R plus gamma times old estimate, right, or new estimate. So, sorry, new state. So we have to do all of that, which we are doing presently. So we need as input the grid, the value function, the policy, the gamma, and the theta. Now, if you don't recall, the gamma is the discount factor. It tells the agent, it tells us how much the agent values future rewards. So we start out by assuming we're not converged, right? And our delta, the difference between the old and new value functions, is 0. So what we want to do is make a sweep over the state space of our environment, keep track of our old v for the difference. This total is going to be how we add up the value for the new state. This weight factor is just the probability from the policy, and since it's the equiprobable random strategy, it's just 1 over len policy state. So if our policy has 4 possible moves in that state, which is what it will have in the beginning. Then this is just 1 over 4. So here we go. Next, we want to do for action in policy state. Next, we have to iterate over our state transition probabilities. This is why it makes sense to do just the state transitions where the probability is 1. So that way this loop is much, much cleaner. So for key in grid.p, we have a tuple of new state, reward, old state, action. We'll call it act because we use action up there, equals key. So next we have to find the entry in the state transition probability that corresponds to the current state and action of our loop. So if old state equals state and act equals action, then we can update our total. Let's scroll down a little bit. Total equals weight times, right, the weight, which is our probability from our policy, multiplied by the probability from the state transition probabilities, reward plus gamma times v new state. Bam. Okay, now the next thing we need is to update our value function, and we need to find out the delta. So it's the max of either whatever delta already is and the absolute value of old v minus new v. And then we need to check for convergence. If delta else false, and then at the end we just return v. That is all there is to evaluating the policy. So now we come down to our main function and we say new v equals evaluate policy grid v policy gamma theta, and then for giggles we're going to print v, and that takes v and grid if I am not mistaken. Oh, sorry. I messed up my nomenclature. It's environment. Perfect. So now we're going to head over to the terminal and see how this does. One moment. And we are in the terminal. So we want to run this. Noisy neighborhood with window open equals bad YouTube video. All right, so let's run it. Aha, there's a mistake. Perfect. So seems like a couple mistakes. So allow me to go bug hunting. Let's go back to our code, and it's in here. What an educational opportunity. So hey, kitty. Okay, so there is our mistake right here. Those are not indented enough, right? Because those have to be calculated for every possible action. It's always something, is it not? Let's go back to the terminal and we will... There we go. All right, now we are ready to do this. So this will take a minute to run. And when it's done, we will have our guesstimates for the value of our equiprobable random strategy. Here we go. So let's do a sanity check first. It's always useful. So we know the top and left rows are the furthest away, so they should have the largest negative values. And indeed, that's what we see. All is well. Next sanity check is that the states nearest to the exit of the grid world should have the best values. So here we get a minus 230 and a minus 206. Perfect. So that is perfectly and totally reasonable. Now you may ask, why are the values so large and negative? It's only 11 moves from the top left to the exit. That's what we discovered in the video series on creating our own environment. And the reason is that the agent here, quote-unquote agent, the solution we're solving in the system of equations takes into account an equiprobable random strategy. That means for any square in the grid world, you could move in any of the 4 directions with equal probability. End result is that you end up bouncing back and forth between states many, many times before ultimately meandering over to the exit. It's kind of a drunken walk type problem. So that is where you get the rather large negative values. So in part, hey kitty cat, in part B, we will cover policy improvement. Policy iteration, which is just evaluation and improvement. And then in the third video, we will cover value iteration. I'm splitting them up because this video is already almost 20 minutes long. So I will see you all in that next video. I hope you enjoyed this tutorial. I hope it was helpful for you. Questions, comments, leave them down below. If you've made it this far, please consider subscribing. I look forward to seeing you in the next video.